Math 2414, Parametric Curves, Video 8. Parameterizations are not unique. First off, you should practice saying the word parameterization and its verb counterpart, parametrize. Some people pronounce it parametrization and parametrize, but I like saying the word parameter inside of there. Call me crazy. So parametrization and parametrize. We haven't parametrized anything yet, but that's around the corner. So what do I mean that parameterizations are not unique? What I mean is if you have a curve or even an equation, with that rectangularly speaking, that there is always, excuse me, more than one way to parameterize it. And to make my point, I've got four similar but not exactly the same pairs of parametric equations. The first one we've already seen. X equals cosine t and y equals sine t. And just a reminder, the way that we eliminated the parameter on that one was we squared both of them, giving us cosine squared and sine squared, and when we added them, we got 1. So in other words, if we squared both equations and added them together, we would get x squared plus y squared equals cosine squared plus sine squared, but that's equal to 1. So the rectangular equation is x squared plus y squared equal 1. And of course, that's the unit circle. No big deal there. But what are these other ones? Well, look at the next one. X equals sine of t, y equals cosine of t. No reason we couldn't pull the exact same moves over here. Square both sides, and when we add x squared plus y squared, we get 1, which is the exact same graph, but with a different parameterization. Under that in blue. So is there really any difference between this pair of parametric equations and that one? Well, the answer is yes, and we'll see why in a moment. But I want to point out that all four of these pairs of parametric equations have the same rectangular equation. The fact that in the third pair, the arguments of the trig functions are 2t is irrelevant in terms of the trig identity. Sine squared plus cosine squared equals 1. So we would still get x squared plus y squared equals 1, even though the arguments have a 2t. It's the fact that the arguments match the 2t's in both of them. And the same thing over here. If we were to square both sides of both equations, because the arguments of the trig functions match, the sum of x squared and y squared is just going to give us 1 again. So what's going on here? We've got 4 different pairs of parametric equations that all have the same rectangular equation and hence give us all the same graph, which happens to be the unit circle. So how could they possibly differ, or do they differ? And the answer is in the orientation. Remember that a parametric curve always has an orientation, which is like thinking, how would the curve trace out as the parameter increases? So we're going to go to Desmos and get the answer to that. All righty. So let's start with the first one, cosine of t and sine. Yeah, I'm just curious what this looks like. Yeah, interesting. Cosine t and sine of t. I'm telling you, you can do all kinds of crazy things with parametric equations. If we were to do that and turn on its graph, it's going to be the unit circle like we expected. It should be dotted, but I think the reason it's not dotted is because we got the range of t values so big that all the dashes are overlapping, but that doesn't really matter. Let's put a point on there, and let's start it here, and let's just go to 4 pi. That's 4 revolutions around the circle. At least that's what I'm expecting. Here we go. It's going kind of slow. We'll speed it up. It's going very slow. There we go. 1 revolution. Excuse me, it'll be 2 revolutions because 1 revolution is 2 pi. Duh. Okay, so this does precisely what we thought it would do. It starts in the at 0 radians, and it just keeps going around the circle. Because remember, in this parameterization of the circle, t is really just representing the angle associated with that point on the circle. So what happens if we go to the next pair of parametric equations? X is sine and y is cosine. It gives us the same circle, but I wonder what the orientation is. Let's turn off the point for a second. Why do you think that graph is what it is? Remember, this is like x equals y equals. Because we have x equals y, but there's a range restriction imposed by sine. Sine can only go between -1 and 1. All right, so we have the same graph as we thought, but let's restart our parameter. Let's take it all the way back and turn on the point. Oh, look, it starts at a different place. When we had cosine and sine for x and y, we started on the positive x-axis. But when we have sine for x and cosine for y, which I know sounds backwards, it starts on the positive y-axis. Okay, different starting point. Oh, and it's going clockwise. So by parametrizing the circle with x equals sine of t and y equals cosine of t, we're not changing the path, we're changing the starting point and the direction of the point on it. So the graph is the same, but the orientation is not. All right, so let's go back to Desmos, and let's go back to Zoom and just make a quick note of what's going on here. When we did the first one, we started over here and we went this way. When we did the second one, we started on the top and went this way. What do you think is going to happen on the next one? Well, x is still cosine and y is still sine, but there's a 2 inside of there. Let's see what happens there. Think about it. Hint, it has something to do with the period. Let's turn the point off so we're not surprised, or we're not, the surprise isn't spoiled to see where it starts. That's interesting. I understand why everything is boxed between -1 and 1, because cosine has range restrictions, but I wonder why it's a parabola, because that's cosine of 2t, hint, double angle formula for cosine. All right, let's go back and put sine t, not sine of t. Oh, interesting, sine of 2t. All right, so this is a circle we were expecting, and where will this start? Let's reset the parameter, and we will start, oh, on the right side again. I wonder if it'll go counterclockwise. It will. Huh. So is there really any difference between this wait a second. Did you count how many rotations it made? How many trips around the circle? 1, 2, 3, 4. Now, why would it do that? Well, because when you put a number in front of the variable inside a trig function, it divides the period by that number. Think of it this way. The period of sine and cosine is 2 pi. If you put a 2 in front of this t, you're doubling the speed at which you travel, meaning it takes half the time to get there. So instead of the period being 2 pi, it'd be cut in half and it's just pi. And since our parameter is going from 0 to 4 pi, it's making 4 periods and hence 4 trips around the circle. 1, 2, 3, and 4. So putting the 2 in front didn't change the starting point, didn't change the orientation, but it did change the speed. So it starts here, still goes counterclockwise, but it's twice as fast. So if I wanted it to go 4 times as fast, I'd put a 4 instead of a 2, et cetera, et cetera. Okay, so it's controlling the speed of the point around the circle. But what about the cosine of x equals cosine of t plus pi over 2 and y equals sine of t plus pi over 2. Let's think about this for a second. Our parameter on Desmos is currently starting at 0, but when we put 0 in here, it's going to kick it all the way up to pi over 2. And where are we normally at pi over 2 on the unit circle? On the top. So I'm going to speculate that we're going to start up here, because the plus pi over 2 already accelerated at a quarter circle. And because it's still cosine and sine, I'm going to speculate that it's still going in the counterclockwise direction. Now, these are just speculations. I'm pretty confident that they are correct, but I've been wrong on easier things than that. All right, so we have cosine of, whoa, that's cool, plus pi over 2, and sine, interesting. It's the line segment we saw earlier, except with a slope of -1, plus pi, and that's that, over 2. And we're at the end of our trip, so let's go back to the beginning. We are starting at the top as I suspected because we moved our starting point pi over 2, which was a quarter circle, and it is still going counterclockwise around the unit circle because x is still being calculated using cosine and y is still calculated using sine. And I think it made 2 trips because we didn't change the period, we just did a phase shift. I wasn't counting. Yeah, there's 1, and then it'll make 1 more trip around. All right, so the moral of this story is parameterizations are not unique. And it's not just for the unit circle. Every rectangular equation has an infinite number of ways to parameterize it. So how do you go from rectangular to parametric? Well, I think that's something we need to look at next.